Hello everybody, welcome into another lesson. So today we are going to talk about the graph of functions. And the first thing we want to talk about here is determining if a graph is a function or not. So this may seem like a review from Algebra 1 and Algebra 2. We have the vertical line test. That is how you can tell if the graph you're seeing is in fact a function or not. So the vertical line test is you have a curve and you take a vertical line at any point on the curve, and if it only passes through one point for the whole curve, if you could take a bunch of vertical lines and as long as they don't pass through more than one point on the curve, it's a function. If it passes through more than one point, even at one point on the curve, it's not a function. So let's demonstrate some of that here. Oh, there's my marker. So let's say we have y equals 1/2 of x squared. So we're going to graph y equals 1/2 x squared. So 0, 0, 1, 1/2, negative 1, 1/2, 2, 2, negative 2, 2. So here is your curve. And let's perform the vertical line test on this curve. Just pick anywhere. And if we look at this curve, we can draw multiple vertical lines, right? Nowhere on this curve does it intersect more than one point. It crosses through only one point on the curve, no matter where you take your vertical line and put it through. So this is a function. So this, in fact, would be a function because it passes the vertical line test. And I got more. Alright, how about this one? X minus y squared equals 1. So let's see, when x is 0, well, that's not going to work because you would get an imaginary number. So how about when x is 1, you would get y is 0. When x is 2, you would end up getting y is 1 or negative 1. And then when x is 3, you would end up getting, or actually let's do 4, 5. Let's do when x is 5, you would end up getting y is plus or minus 2. So here is the graph of this particular parabola. X minus y squared equals 1. You only have to go through one point with a vertical line test, or you could probably even do it by looking at it and tell that this graph fails the vertical line test because it passes through 2 points and not just one, so this would not be a function. This particular case is not an example of a function. Alright, a couple more of these, then we'll move on to actual graphs of functions. So, let's see. X squared plus y squared equals 25. So we have x squared plus y squared equals 25. So we have a graph of a circle with radius 5 with center at the origin. So there's your circle with radius 5, center at the origin. Just go through even one part of the circle with the vertical line test. And you see the vertical line intersects this curve, or this circle, at 2 points instead of 1. So a circle itself, doesn't matter what the radius or center is, will not be a function for that reason. So this is not a function because it fails the vertical line test. One more like this, then we'll move on. X squared equals 2xy minus 1. Is this a function? When x equals 0, well, that'd be an asymptote. That's not going to work. How about when x equals 1? So 1 would equal 2 minus 1. So that would be, let's put this in for x equals 1. You would end up getting 1 equals 2y minus 1, so 2y would equal 2. Well, y would equal 1, so you'll get the 0.11. Alright, let's do when x equals 2. Let's just plot some points here to see what we come up with. So you would end up getting 4 equals 4y minus 1, which means 4y would equal 5, and then y would equal 5/4, so that would be 1 1/4 when x equals 2. Okay, now let's do x equals 3. So that would give you 9 equals 6y minus 1. 6y would equal 10. It's 1 1/4. Alright, so let's see, y would equal 5/3. So that would put you at 1 1/3. So you see it's starting to go up and up and up. Let's do some fractions. Let's say x equals 1/2, right? So that would mean if x equals 1/2, you'll get 1/4 is equal to y minus 1, which would mean y equals 5/4. So that'd be 1 1/4. Let's do x equals 1/3, just for good measure. X equals 1/3, so that would give you 1/9 equals 2/3 y minus 1, which would give you 2/3 y would equal, that would be 10/9. 2y would equal 10/3. Y would equal 5/3. That'd be 1 1/3. So you're going back up again. So here's roughly your graph of this particular curve. And if you do it negatively, it's going to do something incredibly similar. It'll do something incredibly similar down in the third quadrant. Well, if you draw a vertical line, at no point does it cross through more than once, so this actually is a function. This would be considered a function. It's a rational function, so this would actually work as a function. Alright, so that's enough of, that will be enough rather of determining if it's a function or not. Now we're going to go on to what we know for sure to be functions. So, what can the graph of a function tell us about a function? For starters, it can tell us the domain and the range of a function. So let's focus on the domain and range. Let's say you just have any function, for example here. It doesn't even have a label yet. But you just have a function. Clearly that's a function. You can tell its domain and range right away by looking at it. So you notice you actually have infinite x values in the negative direction and in the positive x direction. So your domain, which are your x values, your domain in this case is just going to be the set of all real numbers. Okay, so what about your range? Those are your y values, your outputs. It gets infinitely negative for your y, but it tops at a maximum value of 1. So your range in this case would be from negative infinity to 1 inclusive. So your domain of this, the graph of this function, would be all real numbers. The range is from negative infinity to 1 inclusive. All right, what do we got next? Let me just make sure I'm plotting sufficient points here. 1, 4. Okay. We have 2, 0. I just want to make sure I'm drawing this correctly. We have 1, 0, and then it goes back up. Okay. So this is also clearly a function, right? You could do the vertical line test and it would pass. Now, look at your domain. It keeps going infinitely left in your x values and infinitely right in your x values. So once again, your domain is going to be the entire set of real numbers. Now, what about your range? Well, you notice the same thing. It gets infinitely negative and infinitely positive. So the range in this case actually is also the set of all real numbers. So in both cases, your domain and your range are both a set of all real numbers. All right. Now this is going to shift a little bit. 4. Let me label some points here too. Whoops, I have the x and y coordinates backwards. That's very important. You don't want to mix those up. Here we go. So clearly we have a semicircle, which would be a function. Look at your x values. The farthest left you go is negative 4. The farthest right you go is 4. And you actually have the points negative 4, 0 and positive 4, 0 plotted. So that means your domain is going to literally be from negative 4 inclusive to positive 4 inclusive. Now what about your range? The lowest number you see in your range for your y value is 0. The highest number you see is 4. So your range in this case is going to be from 0 inclusive to positive 4 inclusive. So your domain would go from negative 4 to 4, both inclusive. Your range would go from 0 inclusive to 4 inclusive. Got one more for this, then we'll move on to the next topic about graphs. Now this is a good one. So this one they're trying to trick you. So what is the domain of a function like this? Well, notice we have, it's not defined from the left-hand side at x equals 0, but from the right-hand side it is. So truly your domain is still all real numbers because it goes infinitely left and then it goes infinitely right. So your domain is going to still be the set of all real numbers. Because either way, even at x equals 0, we have a defined value. It's just not defined to the left, but it is defined to the right. Now, what about our range? So we definitely have a lowest value, right? That's going to be, this is the coordinate 0, -3. Well, the absolute lowest value we have of our y's is -3. So in the range, we're going to have from -3 inclusive, and it gets infinitely bigger in both directions. This goes to infinity. So the range is going to be from -3 to infinity. And this, in calculus, we're going to talk about discontinuities. This would be considered a jump discontinuity, since it's not defined to the left for x equals 0, but it is defined to the right. This is also a piecewise function, classic example of a piecewise function, which we'll get into later in this lesson. And if we were talking about limits in calculus, the left-handed limit, it would approach 2. The right-handed limit, it would approach -3 when x equals 0, but the limit overall would not exist because the left-handed limit has to match the right-handed limit in order for the limit to exist. But we'll get into that later in the course. We're not going to do limits today. We'll get into those later in the course, like towards the end of the course. Alright. So we've covered the vertical line test, how to determine if a curve is a function. We've talked about using the graph of functions to identify your domain and range. The very next topic we're going to do is talk about using graphs of functions to determine intervals where the function is increasing, decreasing, or constant. Alright, so let's see here. Let's say we have the graph of f of x equals 3, right? So we have the graph of f of x equals 3. That's just going to be the same as y equals 3. You're just going to get a horizontal line through y equals 3. That just goes on infinitely. Well, the intervals they're asking for are those x values. So in this case, you go from -infinity to infinity. You look, your y values stay constant. It's the x values for which your y values keep increasing, decreasing, or staying constant. We notice from -infinity to infinity, your y value doesn't change. It's a constant 3. So the function is constant. The value of the function is going to be constant for -infinity to infinity. That's the interval for which it's constant. It's never increasing or decreasing. All right. Then we have f of x equals x. This right here is the mother function. A little bit of humor for you, and I won't forget it when my pre-calc teacher in 12th grade in high school said that. The whole class started laughing, and then she did too after she realized what she said. So yes, I did that deliberately to make people laugh. But anyway, we'll talk more when we get to inverse functions about why this is the mother function. But for now, let's graph f of x equals x. So 0, 0, 1, 1, 2, 2, 3, 3. Here, let's just plot some sufficient points here. Let's just keep on going. Trying to draw this as straight as possible. Okay. So there's your standard graph of f of x equals x, right? Well, it goes from -infinity to infinity for your x values, right? And every single value of x you keep putting in, if you keep putting in one more value of x, then the last one, your y value keeps increasing. So in this case, the entire function, the entire value of the function is increasing from negative infinity to infinity. Because you always go from left to right to determine constant increasing or decreasing. And it's certainly not decreasing anywhere, it's certainly not constant, it's constantly increasing from negative infinity to infinity. Now we'll shift things a little bit. And the graph can do all three, believe it or not, and you're going to see where that happens. What about x to the 2/3? So we'll do f of x equals x to the 2/3. So at 0 you have 0, at 1 you'd have 1, and then you go all the way to 8, you would have a y value of 4. We can definitely graph the right branch of this. Now, what about to the left? At -1, you're actually also going to get +1, and then at -8, you would actually get +4. So there is the graph of f of x equals x to the 2/3. Now, if you look from negative infinity right to x equals 0, your y values are decreasing, and it doesn't decrease anywhere else. So the function is decreasing on the interval from negative infinity to 0 non-inclusive. And then it starts increasing from 0 to infinity, from 0 non-inclusive to infinity. So this right here is proof you can have both or even all three characteristics in the graph of the same function. So f of x equals x to the 2/3 decreases from negative infinity to 0 and increases from 0 to infinity. F of x equals negative x to the 3/4. Well, if we remember from Algebra 2, we have an even root, so it's not going to be defined for negative values of x, so we can only consider positive values of x. So let's put in 0, of course. You'll still get 0, but what about 1? You would actually get -1 simply for the fact that it's got a negative sign on it. And then I'm going to have to go all the way out to x equals 16. You know what? Let's make one of these x values worth 2 and y values worth 2. So 0 is still 0. At -1, you'll get -1. Then you have to go all the way to 16. The fourth root of 16 is going to be 2. To the third is 8, and you would actually get -8. So if we look at this graph, from 0 to infinity, it's constantly decreasing. So it is decreasing. Now this time it's going to be 0 inclusive. So when do you include 0 or not include 0? If it goes from increasing to decreasing at the same x value, then you don't include the value itself. That's when you do it, but since this is an even root function, it's only defined for x greater than or equal to 0 for its domain. So it's decreasing on the interval from 0 inclusive to infinity. Alright. F of x equals x times the square root of x plus 3. So f of x equals x times the square root of x plus 3. Well, first, what is the domain of this function? we notice that it's only the square root itself is only defined for values of x, which would make the value of the square root greater than or equal to 0. So x has to be greater than or equal to -3. So let's start at -3 for x. I'll get a y value of 0. Alright, now what about -2? So -2 and the square root would end up giving me the square root of 1 times 2 would give me -2. Alright, and then let's go to 0. 0 for x would give you 0 for y. Now, what about 1? Well, you would end up getting 1 times 4, square root of 4, which would be 2. And then next we could put in 6 for x. Well, the square root of 6 plus 3 is 3 times 6 would be 18. That would put you somewhere all the way up here. So you know what? Let's just put in x equals -1. You would get -1 times the square root of 2. Yeah, you're starting to increase here since you would have negative of the square root of 2. Okay, yep, this is starting to make sense. So you'll be all the way up here somewhere. So let's look at this. You do actually have a bit of a decrease from when x equals -3 to x equals -2. And then from there, it's constantly increasing, right? It's going to be constantly increasing. So we can say that the function is decreasing from -3 inclusive, because that's the farthest left the function's defined for, to -2 non-inclusive. And then it is increasing from -2 non-inclusive to infinity. So that was a rather funky graph, but that's what you get. All right, let's do one more. Let's say, here's a good one, f of x equals the absolute value of x plus 1 plus the absolute value of x minus 1. So we have a double absolute value one. F of x equals the absolute value of x plus 1 plus the absolute value of x minus 1. Good news is your domain in this case is all real numbers. And what a better number to start with than 0. If I put in 0 for each, I'll get 1 plus 1, which would give me 2. Let's put in 1 for x. I would get 2 plus 0, which is 2. If I put in 2 for x, what will I get? So I would end up getting 3 plus 1, which would actually be 4. And then if I put in, let's do x equals 4. If I put that in, I would end up getting 5 plus 3, which is 8. Alright, so from 0 to 1, it's definitely constant, but we still have the left branch to consider. So we know it's going up like this. Now what about to the left? Let's put a -1 for x. You would get 0 plus 2, which would be 2. Let's put in -2 for x. You would end up getting 1 plus 3, which is 4. And then let's put in -3 for x. You would end up getting 2 plus 4, which is 6. And then you just see it starts increasing again when you get to the left of x equals -1. So let's look at this graph here. Very funky graph. So from negative infinity up to the point x equals -1, it's decreasing, right? That's the only interval this function decreases on. From negative infinity, and since we have a change here at -1, it actually goes to constant at -1. You're going to say to -1 non-inclusive. So from negative infinity to -1, for those values of x, your function is decreasing. Then if you look from -1 to +1, it stays constant. So the function is actually constant from -1 non-inclusive to 1 inclusive. And then if you get past x equals 1, from 1 to infinity, the function is increasing. So we've actually had all three occur. So from 1 non-inclusive to infinity, the function is actually increasing. So all three are actually going on here. Okay, so there's increasing, decreasing. Next, we want to talk about minimum and maximum values, which that calculator you see on the screen, that's where this is going to tie in. That calculator is going to tie into this. So let's say, let me just draw an upside down parabola real quick, right? So I'm at the top of a hill here, at the top of the parabola, right? From negative infinity to 0, I'm increasing. And then from 0 to infinity, I'm decreasing again. If you're at the top of a hill, in other words, going from increasing to decreasing, you can think of this like a roller coaster. You're going up the hill and then down it. This is a relative or local max. This is going to be a relative, also known as a local maximum. When you go from increasing to decreasing at a point, at a single point, that is your relative, also known as your local maximum. And then on the flip side, you guessed it, we have a relative or local minimum. Well, let's draw our favorite thing, a parabola again. So you see from negative infinity to 0, my y value is actually decreasing. And then from 0 to infinity, my y value is increasing. I'm at the bottom of a valley. When I go from decreasing to suddenly increasing, I'm at the bottom of a valley. That's my relative or local minimum. So that would be my relative, also known as the local minimum. Well, together, the collective term for your relative, local, or maximum or minimum is called relative or local extrema. That's what your minimum and maximum are called collectively. They're called extrema. And this is where the calculator is going to come in. We are going to find relative, minimum, and maximum values of a function based on using a graphing calculator. So let's do the first function here. F of x equals x squared minus 6x. We are going to find any relative minimum or maximum values. And that will be, I'll show you what that looks like here. So my calculator is modeled after a TI-84. That's what you're seeing on the screen. And you can get it on your phone, actually. You can get it for free with ads, or you can get it for, dang it, Or you can get it for $3.99 for a lifetime, $3.99. It removes the ads and you get all the extra features. So that's something to know. But so f of x equals x squared minus 6x. I'm going to graph that. And look at that. I can zoom out a little bit so you can see more of the graph. You see you have a nice parabola there, as I figured it would be. Now if you touch the extrema feature, and if you look at the whole graph, you see you have a minimum at the point 3, -9. So you have a relative minimum at f of 3 equals -9. That's your relative minimum. We don't have any maximums, as you can see, but we have a minimum at f of 3 equals -9. Now, when we get to calculus, there's something called the first derivative test and the second derivative test that'll help you to be able to do these without a graphing calculator. But we haven't learned derivatives yet, so for now we just have to use a graphing calculator, but even these can aid you in graphing a function. Alright. Let's say we have f of x equals 3x squared minus 2x minus 5. So f of x equals 3x squared minus 2x minus 5. So let's put that in. 3x squared minus 2x minus 5. Let's graph that. And as you figured, probably, you'll get another parabola, hit the extrema, and you see your points. We're going to round this to 3 decimal places. You have only a relative min. You don't have a max, but you have a relative min at the point f of 0.333 to 3 decimal places is approximately equal to -5.333. That would be your relative min. And you can have maximums and minimums in the same function on the same graph. What is the next one? Here's a cubic one. F of x equals 2x to the third plus 3x squared minus 12x. Alright, so f of x equals 2x to the third plus 3x squared minus 12x. Let's see what our relative maximums and mins are. So whoops, I didn't want to do that. Alright, 2x to the third plus 3x squared minus 12x. Let's go ahead and graph that. Let's zoom out a bit here. There's your basic cube function, your basic third power function. You see you're definitely going to have both a max and a minimum. So at the extrema button there, you'll have a relative maximum this time at f of -2 equals 20, but you also have a relative min. You do have a relative min as well. That's going to be at f of 1 equals -7. So you have both a relative max and a relative min in this case. Let's do one more. Let's do a good one here. F of x equals x times the square root of 4 minus x. Let's find any relative or maximum values there. Relative maximum or minimum value. So let's see, we'll take x times the square root of 4 minus x. Graph that. That's a very interesting shape, isn't it? But take your extrema, you only have a relative max, and we're going to round this to 3 decimal places. We have a relative max at f of 2.667 is approximately equal to 3.079. So graphing calculators can be very useful for now for finding maximum and minimum values. The graph can tell you that. All right. And then we can also, let's do a few piecewise functions. So we have piecewise functions. I know we touched on those in Algebra 2 a little bit. So here, hold on, let me make my screen bigger. Or at least let me stop mirroring this. We're not going to need it for the rest of the time. There we go. Let me see if I can make this bigger. I just wanted to illustrate the graphing calculator capability to find maximum and minimum values. There we go. Dang it. There we go. Okay. So now let's talk about graphing piecewise functions. So as you know, with a piecewise function, for certain members of the domain, it'll behave as one function, and then for another part it'll behave as another function. So for example, f of x equals 2x plus 3 when x is less than 0, and it also equals 3 minus x when x is greater than or equal to 0. So this tells you for what values of x, which function this is going to behave as. So what you want to do, granted the top one is x is less than 0. It's not defined for x equals 0, but that it's still important to put x equals 0 into the 2x plus 3. So if you put in the 0 for the top one, you'll get the 0.03 where it's undefined. You're going to have a hole there. This is called a removable discontinuity. And then let's go further left. X equals -1. You'll end up getting -2 plus 3, which is +1. Now, when x equals -2, you'll end up getting -4 plus 3, which this time is -1. And you get the idea how this is all going to shake out with the graph. Now, x greater than or equal to 0, put in x equals 0 for 3 minus x, you actually get 3 for your y, so it actually is defined there. It's just it splits off and behaves like a different function. So let's put in x equals 1. Well, 3 minus 1 is 2. X equals 2, 3 minus 2 is 1. X equals 3, 3 minus 3 is 0. So we see how the function behaves from x is less than 0 and then x is greater than or equal to 0. It behaves as two different functions, and you can get some very interesting graphs that way. And I got more of these. All right. So let's see, we have f of x equals the square root of 4 plus x when x is less than 0, and then f of x equals the square root of 4 minus x when x is greater than or equal to 0. All right. Well, let's look at the square root of 4 plus x. Though it's not defined for 0, it's still important to put the 0 in. You would get the square root of 4, which would give you a y value of 2, so you'll have a removable discontinuity at 0, 2. Now put in negative 1, you'll end up getting the square root of 3, which is a little bit south of 2. Now put in negative 2, you'll end up getting the square root of 2, which is a little bit north of 1. Put in negative 3, you'll end up getting the square root of 1, which is exactly 1. And then put in negative 4, you'll end up getting 0. And you can't go any further left because negative 5 would give you the square root of negative 1. So that's not going to work. Dang it, I butchered it. I missed a point completely. Not good. Yeah, there we go. That's more like it. Okay. Now, what about the square root of 4 minus x? It is defined at x equals 0. You would get the square root of 4, which gives you 2. So that removable discontinuity has been removed. We actually now have it defined at 0, 2. Now, when x equals 1, you would get the square root of 3, which is a little bit south of 2. When x equals 2, you get the square root of 2, which is a bit north of 1. When x equals 3, you get the square root of 1, which is 1. When x equals 4, you get the square root of 0, which is 0. And you can't go any further right because if you do 5, you get the square root of negative 1, which isn't defined. So there would be your piecewise function graph for these two. Let's see here. Let's do a couple more of these. So f of x equals 2x plus 1 when x is less than or equal to negative 1. And then we're also going to have x squared minus 2 when x is greater than negative 1. So it'll behave as a linear function when x is less than or equal to negative 1, and as a quadratic function when it's greater than negative 1. So let's put in negative 1 for the top part here. If I put in negative 1 for 2x plus 1, I get negative 2 plus 1, which is negative 1. Alright, now, what about if I put in negative 2? I get negative 4 plus 1, which is negative 3. If I put in negative 3, I get negative 6 plus 1, which is negative 5, and you see how this is going here. Alright, now, let's put in negative 1 for x squared minus 2. Though it's not defined there, well, negative 1 squared is 1 minus 2 actually gives you negative 1. It's going to overlap with the left branch of this graph, so in this case we're good. Now put in 0, you get 0 minus 2, which would give you negative 2. And then let's put in 1. 1 minus 2 is negative 1. Put in 2, you get 4 minus 2, which is 2. And then you see it turns parabolic when x is greater than negative 1. So you get a nice interesting curve like this. So yes, piecewise functions can be very interesting. In fact, we can even do them in 3 pieces. I'm going to write it over here we have a piecewise function. Let's do that. So f of x equals x plus 3 when x is less than or equal to 0. And then it equals 3 when 0 is less than x, which is less than or equal to 2. And then it also equals 2x minus 1 when x is greater than 2. So here is a piecewise function. So let's start with x equals 0. It is defined for x plus 3. So 0 plus 3 is 3. That'll put you up here at 0, 3. Let's do negative 1. Negative 1 plus 3 would give you 2. Negative 2 plus 3 would give you 1. Negative 3 plus 3 would give you 0. So you see which way this is actually going. Alright, and then let's put in 0 for 3. Technically it's not defined there, but you're still going to get 0, 3, so it's going to connect to the next piece. If I put in 1 for x, I just get 3, and it is defined at 2, so if I put in 2, I'll just get 3. So let's connect that part. There's the constant part. Now, let's put in 2 for 2x minus 1. Though it's technically not defined there, you would get 4 minus 1, which gives you 3. So this is going to connect to the final piece. Let's put in x equals 3. You would get 6 minus 1, which is 5. Let's put in 4. You would end up getting 8 minus 1, which is 7. Let's put in 5. You would end up getting 10 minus 1, which is 9. So there's your piecewise function that is graphed. Now, it is possible that when you graph piecewise functions, you can get jump discontinuities too between pieces of the piecewise function. That does happen sometimes. So if you come up with that, it doesn't mean you did anything wrong. It just means that's how the cookie crumbled. All right. For the final topic of today's lesson, I want to talk about even and odd functions. So we didn't talk about that in the last lesson, but algebraically, and this may seem like a review from Algebra 2, if a function's to be even, that means that if you put in f of negative x, you'll get back the original f of x. So let's do some examples of even functions. So let's say I do f of x equals x to the 6th minus 2x squared plus 3. So algebraically, putting in negative x for your f of x will give you back the original f of x. Graphically, it means it's going to have perfect symmetry with the y-axis. So an even function has y-axis symmetry. It's perfectly even. So we have x to the 6th minus 2x squared plus 3. Algebraically, if I put in f of negative x for this function, I'm going to get negative x to the 6th power minus 2 times negative x to the 2nd power plus 3, which would give me then again x to the 6th power minus 2x squared plus 3. So you see, I got back my original function. So this proves this is an even function. Now, let's graph this so I can show you the symmetry. So at 0, when x is 0, I'll get 3. Now what about when x is 1? 1 minus 2 is negative 1 plus 3 is 2. Then if I do 2, I'd end up getting 60. Yeah, let's do f of 2. F of 2 is going to equal 64 minus 2 times 4 plus 3, so that would equal 64 minus 8 plus 3, which would be 59. So at f of 2, I'm all the way up in here somewhere. And then let's do f of negative 1. I would still get 1 minus 2, which is negative 1, plus 3, which would end up giving me 2. And then if I put in negative 2, I would still get the same thing. I would end up being at 59 for my y value. So here's how the graph of my function is going to work. And that's an approximate graph. I guarantee you it's not that clean cut exactly. This is where a graphing calculator might be better, but look how symmetric it is with the y-axis as an even function. The idea of symmetry is you could take one half of the graph, fold it on top of the other half, and it would stack perfectly even with no overhang. So with an even function, the y-axis acts like your mirror. It's symmetric with the y-axis, perfectly symmetric. Let's do one more even function. Then we'll get into odd functions. So let's see what we got here. Now, here's a good one. So f of x, a much easier one. F of x equals x squared minus 4. Well, algebraically, let's prove this is even. If you put in f of negative x, that's going to then give you negative x raised to the second power minus 4, which would turn into x squared minus 4, giving you back your original f of x. So this is an even function. We've proven it algebraically. Now let's show you graphically. If I put in 0, I'll get negative 4 for my y. If I put in 1, I'll end up getting negative 3, and it'd be the same if I put in negative 1. If I put in x equals 2, I get 4 minus 4, which is 0. The same if I put in negative 2 for x. In fact, it's just going to keep going and going in both directions. So look how nice and symmetric this is with the y-axis. So this graphically is what you're looking for a function to be even. Now let's talk about when you have odd functions. So it's a little bit different with odd. Okay, so if a function's to be odd, algebraically what happens is if you want to take f of negative x, what will happen is you'll end up getting negative of f of x. So if a function's odd, f of negative x would equal the negative of f of x if a function's odd. And graphically, for symmetry, what you're going to have is called origin symmetry. So the point 0, 0 is the mirror. It's symmetric with the origin. Let's do an example here of one of those. Let's say I have f of x equals x to the third minus 5x. F of x equals x to the third minus 5x. Let me algebraically first prove this is odd. So I'm going to take f of negative x. What am I going to get? Well, this would be negative x raised to the third power minus 5 times negative x. Well, that would give me negative x to the third plus 5x. And notice if I factor out that negative 1, I would get the negative of x to the third minus 5x. So I literally got the negative of f of x. So that algebraically proves this is an odd function. Now let's graph this. At 0, I'll get 0. At 1, I would end up getting 1 minus 5, which is negative 4. At 2, I would get 8 minus 10, which is negative 2. At 3, I would get 27 minus 15, which would be all the way up to 12. And then what about if I put a negative 1, I would get negative 1 plus 5, which would be 4. And then what if I put in negative 2, I would get negative 8 plus 10, which would be 2. I put in negative 3, I would get negative 27 plus 15, which would give me negative 12 somewhere down here. So here's the graph of that particular function. And if you look at this, it's symmetric with respect to the origin. You could fold it symmetrically at the origin and it would stack perfectly on top of each other. Let's do one more that's odd, then we'll do a couple that are neither. So let's see here. We're going to have f of x equals oh, let's do x to the 1/3. F of x equals x to the 1/3, okay? Algebraically, let's prove it's odd. So I'm going to put in f of negative x. That's going to give me the negative of x raised to the 1/3. Well, negative 1 to the 1/3 is negative 1, so I'll literally end up getting negative of x to the 1/3, which produces negative of f of x. So this proves algebraically this is an odd function. Now graphically, what do we have? So 0 to the 1/3 is 0, 1 to the 1/3 is 1, 8 to the 1/3, that's 2. So to the right, it goes this way. Now, what about if I put a negative 1, that would give me negative 1. If I put in negative 8, I would be at negative 2, and it goes a lot like this, and it keeps going further down. Notice that symmetry with the origin. That's exactly what you have. It's perfectly symmetric with the origin if it's an odd function. Let's show you a couple of examples of neither. You will sometimes have neither. Of course, if it's neither case, that means then that f of negative x certainly does not equal f of x. It also means that f of negative x does not equal the negative of f of x. So neither of these criteria happen when it's neither even nor odd. So let's come up with an example of that. So f of x equals x squared plus 2x minus 3. F of x equals x squared plus 2x minus 3. Well, let's put in f of negative x, see what we get. That's going to end up being, of course, my negative of x to the second plus 2 times my negative x, then minus that 3, I'll end up with x squared minus 2x minus 3. The only thing that changed is that positive 2x became a negative 2x, but everything else stayed the same, so it's neither even nor odd. Let's graph this. You'll get 0, negative 3. 1, I would get 1 plus 2 is 3, minus 3 is 0. 2, I would get 4 plus 4 is 8, minus 3 is 5. So it's going to keep going up to the right. If I put in negative 1, I would get 1 minus 2, which is negative 1 minus 3, which is negative 4. If I put in negative 2, I would get 4 minus 4, which is 0 minus 3, which is negative 3. If I put in negative 3, I would get 9 minus 6, which is 3, minus 3 is 0, and then you see how this is going to keep going. And it's true, you get a parabola. A parabola by nature symmetric with itself, but it has no symmetry with either the origin or the x-axis, or the y-axis rather, right? You can't fold it evenly over the y-axis or the origin. There's no symmetry. So actually I should write that. There's no symmetry also if it's neither. So that's it for this lesson. Next lesson we're going to do shifts, reflections, and stretches of graphs. So I hope everyone has a great day. Take care.